Hi there, my name is Peter Marshall and welcome to this talk called Aim for Sub-Second Queries. These tips and tricks talks have been created by us here at Imply to share our experience with those of you who are just starting out with Druid. As usual, if you've got any questions, don't forget, register on Druid Forum and we will meet you there. In this talk, I'm going to relate some information about how Druid actually executes queries in its scatter-gather mode. This bit of theory will explain how queries utilise the resources that you provide in a Druid cluster and what the perfect shape for a query using this engine is. But then we'll look at how changes in infrastructure can help make a difference. Or not. So let's get going. What is the ideal query shape for this scatter-gather mode in Druid? Well, the ideal query plays to Druid's strengths, whizzing through a huge flat table at hyper speed. When you're writing your query, you need to think hard about how to get queries into this form. You need to select specific dimensions and measures, use approximations if possible, do it from one table at a time, group by low cardinality dimensions, filter on both dimensions and time, order by dimensions and or measures, and include a limit. But why is that? Well, let's find out. If you want to have good performance from any application, you need to know how the database that's powering it actually works. And this model about query execution in Druid really helps us understand that. It also uncovers the relationship between the underlying data model that you provide and query performance, and it emphasizes why that is. It emphasizes why ingestion technique and data layout are really important considerations when thinking about query performance. Gian Molino, who introduced us to this model, is trying to help us grasp what we can do as engineers to keep Druid performing well, what really matters and what doesn't. We're going to talk through everything that happens after what's called the fan out or the scatter inside each data process. That's in the bottom half of this diagram. And then we'll look at what happens in the broker after the fan in or the gather that happens in the top half of this diagram. Before we set off, just note we're going to be focusing on the model for group by type queries in scatter-gather mode. This is the most common way that Druid is used for lightning fast queries. Scan queries, which is another type of query, work a little bit differently, and it's worth reading about those queries so you know what they are. See the docs to learn a little bit more. And don't forget there are also search type native queries available. Again, go and see the documentation. So let's start our journey together, and we'll start at the moment in the lifespan of a query when it's been submitted to a broker. And the broker and the data processes are then tasked to execute some analytics. When processing a query, it's the one broker leading that query that determines which data processes in your cluster need to do work. That splitting up of the work is called the fan out. The broker maintains a local index of all the segments. It takes a look at our where clause for the time range, along with data clustering that we might have applied through subpartitioning. It decides which of the many data processes that you're running in your Druid cluster it needs to engage with. It knows which segments are available where for the specific time period that you're interested in and the specific subpartitions where you've clustered your data. Only the data processes with segments that we care about are lit up. Taking the lead from the broker, each data process now has a queue of segments that it has to process. And for each segment in its own queue, that process evaluates the where clauses, stripping out rows it doesn't need and finding the ones that it does. This step ensures that only the rows that match the where clauses you've specified are passed up to the next level in this pyramid. If it can, Druid will use indexes in your data to make filtering faster. If it can't, it's going to go and scan the rows. Notice that this part of the processing is where the process also evaluates the time dimension Again, it gives you the specific rows this time that covers the specific time period that you're after. This type of where processing is far more hungry than the evaluation of the where clause by the broker, and it explains why good time filtering and good clustering through subpartitioning and the good use of indexes are so important to help you achieve those sub-second query response times that you can get through Druid. So we've done our filter. Now the process needs to do the hard maths. Those rows that get through that filtering stage now have data from lookups added, and it does aggregations. Order by and limit clauses of the query may be applied here. It depends if the operation is calling for what's called a pushed down limit and order by. As noted here on the slide, it's interesting that an exact count distinct operation is done here. It's treated as a special sort of group by. Remember that this is a queue. The data process is going to split the queue up segment by segment across the computing power provided to this process. It effectively multi-threads the operation. So imagine that there are 12 segments in a queue to process this query. If you've got 4 threads available to the process, it will actually work through 4 segments at a time in parallel. And that means that the results from all those threads now need to be merged before they are passed back to the broker. Despite the scale of data that Druid can handle, at this point we'd expect that group by operation has produced far fewer rows, maybe even just a few hundred than were in the original segments. But there's not just one process involved. Remember, this is a fan out, and that fan out went to lots of processes. And that broker that did the fan out at the beginning, the one that's leading this query, now receives results from all of the data processes, and it also merges them. Now the broker may have to do that limit and order by operation, but it also does halving. If you execute a query in Druid that needs lots of queries to run, say you do a join or a subquery or an in select, Druid kicks off not one of these pyramids, but multiple pyramids. As each result comes in from each pyramid, it merges and finalizes the results over and over again until it has the result that you need. So let's summarize this down. Let's take this a different angle and let's think about it in terms of SQL. Right at the bottom there, you can see that where clauses are evaluated both in the fan out at the broker using those time and data clustering in subpartitionings, and it's also evaluated in each individual process segment by segment. Lookup and group by are next. Then there's a merge segment by segment inside the data process. Then there's another merge, this time data process by data process inside the broker, and then halving is applied. And then right at the very top, merges from individual pyramids. So that's individual subqueries, joins and in select statements are merged in the broker. Now you know what makes a good query for Druid and how you design your schema for those queries, let's take a look at the infrastructure, because surely you might imagine to make performance better, all you need is a bigger, more powerful triangle, right? Well, not necessarily. We need to think about how query performance is constrained and improved by the electricity and wires and blinking lights and spinning disks. First of all, bring your mind back to that fan out, which is when the segments are selected based on the partitioning by time and those clusters of dimensions in your data in subpartitions. The number of data processes that you have overall and the amount of data you have residing on each that could be consulted comes into play here. Given the length of time you're going to scan, for example, imagine how your work will get split up. And what's the ratio of available threads to the number of segments that you have on each process, for example? Can each process handle the queue that the broker is going to throw at it? Data balance across your cluster, as well as your rules for data replication, are also important here. Now let's go into each of the processes as they process each segment. The job of working through the queue of segments is handled by multiple threads. One thread handles one segment each at a time, processing each one until the queue is empty. Now that means you can scale up all of the filtering, all of the aggregation operations up to the number of segments that will be scanned. Here, the more threads, and therefore the more cores you can offer, the greater the performance. But remember that you can't bend, unfortunately, the laws of physics. Providing 30 cores to this process to speed up a query that only uses 10 segments does nothing for you. Only 10 threads will be created, one per segment. Rather, a common constraint to you in this situation is the time it takes to process each segment, the segment scan time. And that is why right sizing of segments is really important. Too big, there'll be a slow scan time. Too small, and you'll create a massive overhead. When segments are opened, also bear in mind that Druid uses OS level memory mapping, using all the available memory in the cluster. So commonly used segments then could be in memory already, which leads to further speed improvements. But if you don't have much OS memory available, memory mapping will not be as effective. Before we go on in this presentation, if you do see Jetty anywhere, including in the documentation, it's the name of the software component that Druid is using for its web services. Jetty is very often used for exactly this kind of machine-to-machine communication, especially in distributed systems like Druid. And this send step, when all the segment data is merged inside each process and prepared to be sent back to the leading broker, happens inside one thread. While a data process can access lots of resources for segment processing, this merge step is craned to just one thread inside this process. Now, most of the time this is fine because the design is to deal with much less data than you have in your original segments. But what if it's not? What if the output of the previous steps in this process is millions of rows? Like if you do a group by a high cardinality dimension. If you do that, you return just as many rows as the raw data had to start with. In those situations, you're returning tons of rows from each segment, and that very quickly accumulates. And as this is constrained to just one thread inside this data process, it doesn't matter how many cores you have available to this process, it will get bottlenecked here. And this is not a problem, therefore, that you can solve by adding infrastructure. The next phrase, now let's look at the broker, where it's going to combine the results from each of those data processes that it fanned out to. And this merge operation uses all of the cores available inside the specific broker that's running this query. The workload, therefore, is heavily affected by the volume of data that's bubbling up from lower down in the pyramid across all of the data processes. And that means, of course, the number of processes that you need to merge results from also has an effect. This merge operation happens within the broker that's leading for this specific query. This is the one that's leading this query. It did the fan out, it's going to do the fan in. This has an important implication. That means you can't scale one query across multiple brokers. This final step of query execution occurs in one broker. Adding brokers, therefore, doesn't solve bottlenecks that occur in this layer, but it does help to increase the overall capacity that your cluster has for concurrent query execution. Instead, what really helps at this layer is scaling a single broker up, especially when you have high row count queries. Now let's go to the finalized stage after the data has been merged by the broker. We've just got one more step. Now, this, just like the final step on each data process, happens in just one thread. That's in just one Jetty thread per query on the broker, and it is a final bottleneck. Neither adding more cores nor adding more brokers is going to help you solve a problem at this layer. So for example, adding more cores to try and fix a slow having clause may not help you. And let's not forget those big join operations, those subqueries, those in-select statements, when multiple pyramids are all executing. That ends up in this single thread too. And that's exactly why there is a configurable limit with a default of 100,000 rows to keep the lid on this very final step when you are doing join subqueries and in-select statements. Now let's put this together with the roles that we had from the beginning. If there is no time clause in your where, or your queries cover really long periods, that immediately sets things off to a bad start. You should always apply some kind of filter, making good use of indexes and of clustering through subpartitioning to speed up that fan-out process, pruning. Think about what the cardinality of the grouped by dimension is. Low cardinality doesn't mean 15 values, don't be worried, but you do need to think about how many there will actually be. You could hit a bottleneck here. You might even consider using some kind of tactic to reduce the cardinality of your dimensions. Maybe you'll truncate values or strings and so on. And you might use an approximation technique like Apache Data Sketch hyperloglog for count distinct, or theta sketches for count distinct and set operations, or the quantile sketch for distributions and so on. Think about whether to use a limit. And now you can appreciate that queries with subqueries are merged at the top in a single thread. Use those with particular caution. We want to shape our data so that our query is referencing a single table. That means enriching tables at ingestion time or even upstream, rather than trying to do complex joins at query time. If you want to know more about this group by engine in extreme level of detail, including the question of whether limits and orders are pushed down, do go and take a look at the group by query page in the documentation. Keep this visualization of how Druid executes queries in mind as you go and design your SQL and look at query performance. When you're looking towards those sub-second queries which Druid is designed for, this is a really helpful model to keep in your head. For ultimate speed, shape your data in one table and allow most of the filtering to happen at the fan-out stage. If you've got any questions about what you've seen today, register on Druid Forum and raise a question. Say hi, we'll say hello to you. Visit learn.imply.io for Druid related courses. And of course, with me, please say thank you to the developers behind Apache Druid by putting a star on that Apache Druid GitHub repo. Thank you.